Good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lectures. Today we want to, in thermodynamics, look at efficiency of diesel engine. Now, diesel cycle over diesel cycle. Diesel cycle basically has two isentropic processes or adiabatic reversible processes. That is isentropic compression, that's step 1 to 2, and it also has adiabatic expansion, that is step 3 to 4. And then we have insertion of heat, that is at step 2 to 3, where we have the compressed air, which is now at high temperature. Fuel is injected, then ignition takes place, and of course 4 to 1, where we have exhaust system, where there's rejection of heat at that particular process. Let's just sketch it quickly so that we remember in passing. That is pressure, cylinder, pressure, and then we have cylinder volume. So we have this process 1 to 2, 3, 4. Those are state points. 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So we have fuel injection, this particular point, and Q also in the system. Here we have Q out. This is isentropic compression. This is isentropic expansion. And both these two processes are adiabatic. It's a diabatic. This one also is a diabatic. Diabatic processes. Now we want to focus on these two processes here. We want to focus on this process and that process here. Now, we have defined efficiency for these heat engines. Heat engines as neta as being 1 minus Tc over Th. That's the high temperature, the higher temperature, and the cooler temperature. Th is high temperature, C is the lower temperature, corresponding to the temperatures of the reservoirs. So that is a general expression for these particular quantities. So let us use that. There's thermal efficiency. Thermal efficiency. This is efficiency, that's symbol neta. We're calling that symbol efficiency. Now, let us work on the step 1 to 2, where we have adiabatic compression of the gas. Compression of the gas, of course, once compressed, high temperature, fuel is injected, then there's ignition, because remember, this is a compression ignition engine, not a spark ignition engine. That one we have discussed in the Otto cycle. Now, let us look at these quantities. If we go to first law of thermodynamics, we have du is equals to dq plus dw. And so we have said that if we assume that the fuel, that's the fluid in this particular system, behaves like an ideal gas, then we can use the characteristic equation of ideal gases or ideal system. PV is equals to nRT. And also we are realizing that step isentropic compression is an adiabatic reversible process. So dq is 0. Therefore, du is equals to dq plus dw, and that is 0. But remember, also we know that for ideal systems, du is equals to cv dt, because in the total derivative, the exact differential for du, which we have said is du is del u del t dt of v plus del u del v dv of t. This coefficient here is 0 for ideal systems. Therefore, we are left with du is equals to cv dt. So that if we plug in these quantities in the first law of thermodynamics, then we have cv dt is equals to minus p dv. That's the expression for PV work. These are PV work. We have the piston, cylinder, and we have the reciprocating work and so forth, output and so forth. Now, if we assume that we have the lower temperature corresponds to our initial state, the higher temperature corresponds to our final state, then we can insert the expression for pressure there. So we have cv dt is equals to nr minus nRT over v dv. Because if we divide by t throughout and rearrange these quantities, then we have that cv over nr dt over t is equals to minus dV over V. So we can integrate, like we have said, from some initial to some final state. So I is initial state, F is some final state. So in terms of temperatures, I will be the lower temperature, F will be the final state will be the higher temperature. In terms of pressure, the same description takes place. So if we call C as CV over NR, then we'll see that 1 over C is equals to gamma minus 1. This gamma minus 1 is the ratio of the heat capacities. We have talked about it quite extensively in our earlier lectures, so please I encourage you to go through those earlier lectures so that you get the ideas, the concepts, and the ideas systematically. Now, gamma over CV. So that is true because if you put gamma as CP over CV, just put there 1 over C is equals to CP over CV. You will see that will be CP minus CV over CV. For ideal system, that is NR. And so we have NR over C over CV, which is basically 1 over C. So C is CV over NR. Very, very easy to see that particular expression there. So what quantities do we get? So we get C, natural log of TF over TI is equals to minus natural log of VF over VI. Remember, when we remove that negative quantity there, we invert the quotients there. So if I remove the minus sign, then the VF will become the denominator, VI will become the numerator. So I'm going to use that identity C in TF over TI is equals to natural log of VI over VF. Secondly, to remove that C, which is multiplying that log quantity, I can take it as an exponent. If I have M to the natural log of Y, then it can be expressed as natural log of Y raised to power M. So we just have natural log of TF over TI raised to the power C is equals to VI over VF. So we are getting there, we are getting there. Now, let us continue further to develop the expression which you want to use in computing the efficiency. So, we have that as natural log. We have forgotten natural log here. We have natural log of that. So, natural log of TF over TI raised to power C being equal to natural log of VI over VF. That means that this quotient here is the same as that quotient there if that expression has to be true. Natural log of M is equals to natural log of N means that M is equals to N. So we can say that TF over TI raised to power C is equals to VI over VF is equals to VI over VF. And so to remove this exponent, remember VI of VF is raised to power 1. We divide the exponent by C, so we get TF over TI is equals to VI over VF 1 over C. We want it as 1 over C because we have already defined 1 over C as being gamma minus 1. So we want to bring it in now. So we have VI over VF into gamma minus 1. This is the expression we want to use extensively in this efficiency calculations. So now that we know that this is true, that is true, so if you have T2 over T1, then it will be V1 or V2 raised to the power gamma minus 1. So let's now focus on those processes in the diesel cycle where work is done. Work is inputted, and the compression process, when you're compressing the gas, work is inputted in that compression process. When you have expansion, work is done on the piston. Pushing it is down. So those two processes, we have work input and work output, and then we have that portion 2 to 3 where we have the ignition, where the fuel is injected into that compressed air. Now, let us work with the process of isentropic compression. Remember, it's that process from state 1 to state point 1 to state point 2 in that diesel cycle. Just remember in your mind, we have drawn it, we just erased it. Now, that's isentropic compression, which is an adiabatic reversible process. It's an adiabatic reversible process. So for that step 1 to 2, 1 going to 2, we have T2 over T1 will be given by V1 over V2 to the gamma minus 1. So we are getting there. Already we are seeing the volume relationship at that particular point, and this V1 over V2 is the compression ratio. RP is equals to V1 over V2. Therefore, we can say that T2 over T1 is equals to RP raised to power gamma minus 1. Raised to the power gamma minus 1. In terms of efficiency, remember, in terms of efficiency, where we have said this is 1 minus the temperature of the cold body divided by temperature of the hot body. Now this is hot over cold, so we have to invert it. Therefore, T1 over T2 is equals to 1 over RP into 1 over gamma minus 1. Because the efficiency, we said, was 1 minus TC over TH, which is 1 minus T1 over T2. So if we plug in that out, the thermal efficiency of that particular process will therefore be given by 1 minus 1 over RP 1 over RP into 1 over gamma minus 1. So we have related the two the temperature there at state point 1 and state point 2 to the compression ratio, and the efficiency of that particular process there is 1 minus RP 1 gamma minus 1. So the step 1 to 2. Now we have the 2 to 3. 2 to 3, which is an isobaric process. Isobaric process. And where we have heat inputted. That is step 2 to 3. In this step 2 to 3, why are we interested in it? It has the cutoff ratio. We introduce the term cutoff ratio alpha. And that cutoff ratio alpha, and I always want you to remember that in certain cases they talk of the ratio of heat capacity Cp over Cv as kappa. But I don't like using kappa because kappa also is isothermal compressibility, which is another very important quantity. And alpha is isobaric coefficient of thermal expansion up times V, which is also another very important quantity. So avoid using overlap of the use of the symbols. So alpha is V3 over V2. Alpha is V3 over V2. So again, applying our expression here, which you have gotten there, which is our fundamental expression, therefore T3 over T2 will be given by V2 over V3 gamma minus 1. Gamma minus 1. So we have that quantity there. And of course, that is the compression ratio. So we can say that is alpha into gamma minus 1. Alpha into gamma minus 1. So, again, for that particular process, efficiency of that particular process, 2 to 3, we have 1 minus T2 over T3. 1 minus T2 over T3. So we just proceed the same way, just inverting the quantity. So we have 1 over alpha into 1 over gamma minus 1. So it becomes 1 minus 1 over alpha, 1 over gamma minus 1. 1 into alpha, 1 over gamma minus 1. So if we try and consolidate, these particular quantities, then we can pick on can use a permuter. You can permute T3 over T2. Let's call it T2 over T3 over T2. That will give us T3 over T1 into T1 over T2. This particular quantity there, that particular quantity there. And remember, in that particular quantity, we have said it is V2 over V1 over V3 into gamma. Let me just write it properly. We have said T3 over T2 here is equal to alpha into gamma minus 1. Alpha into gamma minus 1. And so we are also saying it is the same as T3 over T1 into T1 over T2. What did we get for T1 over T2? We got 1 over the compression ratio to gamma minus 1. So we have 1 over compression ratio into 1 over gamma minus 1. So in this relationship here, we can quite easily isolate and say that alpha into gamma minus 1 is equals to T3 over T1 into 1 over R P 1 over gamma minus 1 over gamma minus 1. So these quantities are related. This ratio here is related to this particular ratio here in the manner which you observe. So we have the cutoff ratio, and here we have the compression ratio. Cutoff ratio with compression ratio. And of course, you see that if you simplify it further, then you'll have alpha is equal to T3 over T1 raised to the power 1 over gamma minus 1. And of course, this will be dividing by that, so it's 1 over gamma minus 1 squared. So we are able to relate the cutoff ratio and the compression ratio. Now, I want you to look at this element here, T3 over T1. T3 over T1. I want you to look at that element there, T3 over T1. Remember, in your circle, we have cylinder pressure and you have cylinder volume. And so we have our system state point 1, state point 2, state point 3, state point 4. Remember again, I repeat, this is compression, isentropic, this isentropic expansion. Remember that. This is injection of heat and also fuel injection. And here we have the exhaust Q out. Now, look at T3 and T1. T3 corresponds to this point. That is the temperature of that fuel when it is ignited. We can call it the flame temperature. So we can call it the adiabatic or flame temperature. Think of it as the flame temperature. That's the temperature on ignition as T3. And we can call this the temperature of the inlet gas. This is the flame temperature, that fuel which is being ignited at that point. Remember, it burns down, releases products which are at high pressure. They work on the piston, they push the piston down. From the TDC, pushes the piston down. Of course, and during that particular process, you have the reciprocating motion, which of course goes into translated finally is outputted in the appropriate torque which is required, which affects all those transmission and movements and so forth and so forth. Now, that is the temperature of inlet gas, the temperature of outlet. So we have that expression relating those two temperatures there. Those two temperatures there. And of course, you know that this one will be much, much greater than that inlet temperature, that combustion. So you just note that we can get this relationship here, relates inlet air temperature to the flame temperature. Now, finally, we want to look at processes 1, 2 to the processes again. We have the process 1 to 2, we have 2 to 3, and we have 4 to 1. Remember these processes, this is constant volume. Therefore, delta V is equals to 0. And this process occurs at constant pressure. Occurs at constant pressure. So, we know that heat transferred at a constant pressure. We have dH, if we work with our quantities dH, dC squared over 2 plus G dZ, that is equals to Q plus W. If we assume that kinetic energy is negligible, 0, and there is no change in the datum level or reference level, 0, so dH basically is Q plus W. And for adiabatic processes, that is 0, so dH is equals to dW. Sorry, that's dW. So, at this particular portion there, and remember dH is equals to Q, heat transferred under constant pressure. Under constant pressure. This is a thermochemical observable, that's a thermodynamic state function. We have already talked about that, and that's a very important link. That's a thermodynamic state function. That's a thermochemical observable. Remember, thermodynamic state function, thermochemical observable, this is a path function. So it's very important to remember all those. So heat transferred at constant pressure, already you know we're talking about enthalpy. So the work associated, the work for that particular process there will be H2 for process. So process 2 to 3, we have W, H2 minus H1. And so, what is H2 minus H1? dH, we remember, is Cp dt. Cp dt. So, we can link that and say W is Cp temperature 3 minus temperature 2. And for this particular process 4 to 1, process 4 to 1, where we have rejection of heat, where heat rejected, and of course when it's rejected, it can be rejected, those gases, you can go to the exhaust port and they'll come out of the exhaust systems, or it can be taken up by the cooling system of the engine, because you have a coolant in the system. You have a radiator, just a coolant which is able to take some of the heat, so the engine is not affected too much by those kind of temperature changes. Now, so heat rejected. Now, at that particular point, remember we have said this is constant volume. Again, heat transferred under constant volume is the change in internal energy. It's a constant volume process. Remember, constant volume. Therefore, heat transferred under constant volume is the same as internal energy change. Internal energy change. So, what are we saying? So, we are saying that the heat transferred here for this particular process, here where we have that, is the same as the internal energy change, and therefore du is equals to CV dt. And so that will be CV into T1 minus T4. Now, in terms of heat, remember we had said for first law, because du is 0 for that cycle process, then W is equals to Q. That is, W is equals to Q. So we can express the efficiency, which we said was W net over Q in, as being Q in minus Q out over Q in. And so neta, which is the efficiency, neta, which is the efficiency in this particular case, so the neta there, plus combination of the processes there, will be given by 1 minus Q out over Q in. Q out over Q in. And so what is Q out? Q out, we have said, so that will be 1 minus CV into T1 minus T4 divided by CP into T3 minus T2. And what is this expression there? What is that expression there? That expression there, remember we've said Q out, CV, T4, CP, that, remember, gamma is CP over CV. Therefore, neta here is 1 minus 1 over gamma into T1 minus T4 over T3 minus T2. So, we have seen the work done in those particular sections related to the heat capacities, and that is for process 2 to 3 and process 4 to 1. We can relate them to these particular quantities because we are dealing with some of those particular quantities. We don't need to mention because the mass flow rate MF, which will be here, which we put here as mass flow rate, and here also, where are we? Mass flow rate. Of course, the two will cancel out, so we don't need to worry about it. That's why we didn't carry them through, because they end up canceling out, and we'll have that expression then for that efficiency in that particular system. So we are able to see these efficiencies associated with these processes in this diesel cycle. So we'll stop at that point.